So I thought the best thing to do was really just to go through the example there. But on the back, I will show you some example of this, but we can't run on the back end. We had to set this up at very short notice. But if I just go to the, I'll do the Fortran version for the moment. So if I do, if you look at the hello.f90, it's just use MPI implicit none init IRA, MPI init IRA, write hello world, MPI finalize. So it's really very, very straightforward. But if we just compile and run that, I think we saw this. MPI F90 minus O hello hello.f90 and MPI run minus n4./hello. We see hello worlds, but we don't know who they are. So what we want to do is to put in some. I'm going to make the foolish mistake of doing live coding here, and I've got this nasty highlighting. But anyway, so we need to basically have an integer for the rank and the size. Okay. I want to do a couple of things here. I want to print before MPI init, and then after this we'll do call MPI com rank of MPI com world rank IRA, and we also want the size. Okay, so that should work. Probably not going to know. Let's see if that works. We can rerun it. So as you see, hopefully it's obvious. The first thing is that you get 4 hello worlds before MPI init. So it's really, really important to recognize that it's the MPI run command that launches multiple processes. Okay, you can MPI run anything. Okay, oh actually, so if I do, let's do ls minus l readme. Okay, I can MPI run minus n4. Oh, I don't know if that's going to work. Yes, it did. Okay, so it ran the command ls minus l 4 times. It just launches multiple processes. It doesn't do anything magic. Okay, but it happens. So you know, but if you call MPI init, they're then brought together into a single MPI com world. You can do stuff. Okay, so you know there are 4 processes running right at the start. Okay, so if I just do what I really wanted to do, MPI run minus n. Oh, I didn't want to do that. Sorry. ./hello. Okay. So of course we probably don't want lots of. What was the next exercise? I should get the sheet up. Rank the source number of processes. Okay, so it's very annoying. If you imagine I was running this 1,000 processes, I get 1,000 prints. Okay, so that's not really going to work. So typically, we would, if we want prints, we would do something like the number of processes is size. Okay, so if I run that. Okay, that's just a debug message. Because we don't want it printed out multiple times. So typically, okay, we do if rank. Now we can do anyone to print, but conventionally, we pick rank 0 as the boss. It's very important. There is nothing, really, almost nothing special about rank 0. Okay. Okay. So let's be very clear. Every process executes that statement. Every process, if it executes the statement, if rank equals 0, it happens to be that rank is only true on one of the processes. Okay, right? There's nothing magic about that statement. Okay, there's no, you know, but it does what we want. So just a quick question: there is no special. There is no speciality to rank 0, but we typically pick rank 0 to do print statements as the boss. Why do you think we pick rank 0 as the boss? not rank 7 or rank 252. Yes, there is always a rank 0, absolutely. So if you run on one process, there is still a rank 0. So it is a sensible thing to do to do. Okay. So the other thing you might want to do is what was the other question we had here? Yep. Why don't you find an MPI process in your call? Well, let's try it. Let's basically get rid of that. Okay. Sorry. Let's get rid of MPI finalize. So nothing really happens here. It depends on the implementation. So, you know, we're lucky here. What can happen is you can get an error message at the end. But the most important thing is, if there were messages, if we were doing message passing, if there are messages in flight, sending and receiving, you can't just quit because MPI still may have messages to process. So you should call MPI finalize. And what MPI finalize does actually is it basically waits until everybody has got there and then carries on. It allows it to do a tidy clear up. Okay. In terms of the node, let's just make this. Okay. If we want to print out, we use this. It's useful to have this node name, so we can do something like I can't quite remember if it was. So we want to just print out the node name, which is this function MPI get processor name, and we just have to. I've copied that from somewhere. Okay, name, and then let's call it node name. Why do two persons never write and standard out at the same time? I'll come back to that. That's a very good question. I will come back to. I'm about to illustrate that here. Okay, so that's a very good question. Very, very good question. I'll illustrate it. That's in fact what I was just about to do. But let's do call MPI get processor name of node name name len, and it is IR. Rank is on node name of one name. Okay, let's just run on 4. So they're all on next gen IO login too. Now, so I wanted to. So first of all, all the print statements are coming to the screen. Now, these processes are running independently. You cannot assume that does not mean that that rank 1 executed before rank 2, before rank 3, before rank 0. Okay, that is just, these are all printing to the screen, and they just arrive. So if I run again, I'll get a different order. Yeah, 1, 3, 2, 0. So, but that is not. So basically, they're all printing, and the output gets interleaved. But a good MPI implementation makes sure they're never interleaved character by character. So lines will be preserved. So output, if 2 processes write to the screen, okay, they can appear like that, like that, like that, interleaved. But the order of each process's output will be preserved. But they can be interleaved in any way, okay? And that interleaving doesn't mean that which process ran first or second, because it's just, you know, if if I post 2 postcards, they arrive at different times. I mean, this does not have any relation to what time they actually run. However, the output from a single process will appear in order. And as Laurent points out, it's a good MPI implementation needs to leave them on a line-by-line basis, so you don't get things meshed up. Okay? Does that make sense? I don't know if that answers your question. Now, of course, these are all running on NextGen IO login 2, okay? And so it doesn't matter how many run on. Now, over the lunch break, I contacted my colleague Adrian, who actually gave me a script which allows me to run on the back end, okay? Now, that is a bit, okay, so I did something very stupid. I accidentally deleted the script. So I will have to recreate it. I was messing around. It was called hello.job. So we need to do, it's some sort of magic here. I will set this up. I've only just got it working because I've not used this system before. But I will, there's a bit of jiggery pokery to do, but I will so just, oops, yep. So we have to do some setup, but basically this, a batch script just says, so what we can do is we can run, now, PPN is processes per node. So what this is saying is, I'm going to run on the NextGen IO system where there's lots of compute nodes. I'm asking for 1 node, okay? I'm saying I want to run for 1 minute. Let's call it hello. These are all magic options. You can just ignore these. But basically, I'm running on 1 node and I'm running 48 processes, okay? So it's LL, no, it's not, it's sbatch is the command, sbatch hello.job. That will run on the back end, okay? Does someone have a question? Well, okay, so Laurent, well, that's because a good MPI implementation makes sure that the output is only buffered on a line-by-line basis. So each line is written atomically, okay? So that's just because, well, of course, also the output is being mediated by the MPI run program. Actually, when your processes print, they're printing it, and the standard out is going to MPI run. So there's a program called MPI run which is running, and it is actually mediating the output and making sure that it's done on a character by character basis. Does that explain it? Fine. So if we look, we should now have an output. If we look at slurm, it's 216.out. You can see NextGen IO, compute node 19. Now they all ran on compute node 19, okay? Not surprisingly so, but if I now ask for 2 nodes, okay, I run for 96 processes, and I do 48. Now each node has 48 cores, so I'm saying I want to run 96 processes, and this magic says I want to run 48 on each node. That's processes per node. The important point is this is going to run across 2 nodes, okay? Let's again. It's run very quickly, and if we look at slurm 25617.out, you will see that the low numbered ranks 0 to 47 will be on CN19, but the higher numbered ranks somewhere there, CN27. Okay, so you see rank 90. You can see that we've got different. You can't see my cursor, which is a bit weird, but you can see that we run on more than 1 node. For example, okay, so if I grep CN on that, you will see that, yeah, node 1, they're all on the low numbered node, so it put ranks 0 to 47 on the first node and 48 to 95. I can put that into sort actually. This will probably be, well, doesn't quite work, but you can get the picture, okay? So that's actually why printing out the node name can be useful. So each node of NextGen IO is a 48 CPU core shared memory node. So they all have the same host name, but the different nodes have different names. So hopefully that was reasonably useful. Does anyone have any further questions about that exercise. Actually, so in fact, if we look, PPN is a fairly standard argument, so there's an awful lot of verbiage there. But in fact, maybe if I just edit it and say, well, I just want to run 6 processes, but I want only 3 processes per node. Okay, well, let's do a bit more exciting. Let's do 4 processes per node. So I would expect ranks 0, 1, 2, and 3 to be on node 1, and then to ranks 4 and 5 to be on the second node. Okay, let's see if that actually works. I'll put this back script up on the website over the break, so you'll be able to do this yourselves. And we look at slurm25618.out, and what did it say? Yes, so you can see that here we are. Rank 5, 4, and 5 are on CN27, compute node 27, and 0, 1, 2, and 3 on compute node 19. And none of this layout where they run has any effect on the correctness of your program. This program would run exactly the same on the front end as in a, but it's useful to know where they are. And of course, the speed would be affected by the node location. Okay, so if there's no other questions, I'll actually go on to the first talk. We talk about any kind of real MPI. So I just get set up for the next lecture if I get the right window. So I kind of often say this lecture is really important at the start, but these first few lectures are very important to understand the concepts, okay, which we've done, then to understand the basics of MPI and how to initialize, to do a hello world program to understand what goes on. And then what we're going to do now is actually going to talk about messages, okay? We're actually going to talk about how we, should share my screen. So you should be able to see that fine. So we're going to talk about messages. The fundamental way that MPI works is you send messages between processes through send and receive, and that's what this lecture is going to cover. So in MPI, a message contains a number of elements of some particular data type. Now, there are basic types and derived types. The basic types are the types which exist in the language. So you can by default send in C ints, characters, floats and doubles, or in Fortran Booleans as well, and complexes, because they're defined in the language. You can build up derived types, which are more complicated objects. There's a whole lecture on that tomorrow. But for the moment, we'll just talk about the basic types. Now, this is one of the few places where C and Fortran diverge, because of course, Fortran and C have different types. So in MPI, the MPI types are different. So every time, it turns out that there is only one send routine. There's not an MPI send int, MPI send char, MPI send double. There's an MPI send. Because MPI is a library, okay, it's not a compiler, it's a library. When you call the function in old-fashioned languages like C or Fortran, the function that you call gets no information about the type, okay, in old-fashioned Fortran at least. So when you call a send routine to send data, you have to tell MPI what the message is, okay? So there's a special flag you pass to MPI saying, these are integers, these are doubles, these are longs, these are floats. It's just a constant, okay? But it will become more obvious when you see exact examples. But in C, if you want to send floats, okay, then when you call the send routine, you have to say MPI float. If you want to send doubles, you have to say MPI double, okay? If you want to send integers, I want to say MPI int. Okay, so for every type in the language, there's a magic number, a constant in the MPI library, which maps onto it. So for scientific and technical programming, you'll only ever use ints and doubles, to be honest. Fortran has a much smaller, but for scientific and technical programming, much more useful set of types. Integers, reals, double precisions. This is a horrible syntax. Complexes, logicals, and characters. Byte I won't talk about. We try and avoid talking about bytes in MPI. I've also avoided doing characters in Fortran. Characters are a nightmare in Fortran. So unless you really understand the difference between an array of 7 characters and a character string of length 7 in Fortran, then you should steer clear of them. But those are the types. If you're a Fortran 2008 programming, you'll immediately ask, well, Fortran 2008 has a much more rich type definition. It allows you to ask for a variable without specifying the type, to say, give me a variable which is big enough to hold a number of this size. It's done sort of dynamically. I'll cover that later, but this is just for basic programming. So having done the types, if you didn't understand that, it's fine, because it'll be obvious when we see examples. Point-to-point communication. Okay, point-to-point communication is communication between two processes. It's like sending an email, making a phone call. It's not collective, we're just doing point-to-point. You have a sender and a receiver. It's a communication between two processes. The source process, which is the one that calls the send, sends a message to the destination process. The communication takes place within a communicator. So we will be working with an MPI COM world, which means that any process can send to any other process. But if you were sophisticated and you had split MPI COM worlds into two halves, say odd and even processes, then within MPI COM odd, you could only communicate with odd processes. With an MPI COM even, you could only communicate with even processes. And the destination process is identified by its rank in the communicator, which is a number between 0 and n-1, where n is the size of the communicator. Okay, so the ranks are numbered individually, but they're indicator. So the way it works is in point-to-point messaging MPI, the sender calls a send routine, specifying the data that is to be sent. So this terminology is very important. This is called the send buffer. Again, buffer, it sounds like fairly old terminology. It's just an array, okay? Think of it an array, but MPI calls it a buffer, but you can call it an array if you want. So the sender calls a send routine, specifying the data that is to be sent, and this is called the send buffer. The receiver calls a receive routine, specifying where the incoming data should be stored, okay? And this is called the receive buffer. So the data goes from the send buffer on the sender to the receive buffer on the receiver. However, when you send a message, MPI also creates some envelope information, like where it came from and other information, how long it is, bits and pieces like that. That is received separately. So the receiver also, it's created automatically on the send side, but on the receive side, the receiver has to receive the metadata into separate storage. And MPI calls this the status. So the sender specifies a send buffer with the data you want to send. MPI packages that up into a message which has a header with metadata and the data. On the receive side, you specify two locations when you specify the receive. The major one is for the data, the receive buffer, but you also have to specify somewhere for the metadata to go, which the MPI calls the status. Okay, so hopefully that's clear. I've lost track of the chat. Okay, fine. Now the communication modes, MPI has a number of communication modes. It has, now this is where it gets slightly complicated. I have the final lecture of today will go into this in some detail, but you can send messages synchronously in MPI. This only completes when the receive has completed. That's like making a phone. As I said, when you do synchronous send, you issue the send and you wait until somebody you issue the send, and then you wait until someone issues the receive. Okay, so if there's no receive issued, then this is guaranteed to block. A buffered send is exactly equal to what I said was asynchronous. It always completes unless an error occurs, irrespective of the receiver. So buffered send is MPI's name for an asynchronous send. So synchronous send is called synchronous send. Buffered send is called asynchronous send is called buffered send. So if you think about it, if I said I've declared an array of size a megabyte, okay, I send that off to somebody, okay. If I send it synchronously, okay, I wait until the receive happens, and then obviously I can then reuse that data, okay, because it's been received. If I do it more like in an asynchronous way, I say to MPI, could you please send this megabyte of data, but just send it. I don't care when it gets there. Just send it off, and you know, I'll just trust it that it gets there. Okay. I then want to reuse that data. Okay. because I can't just leave it lying around. But how do I know if I can reuse it? Because I never know when it's been received. So what is the only safe way you can implement asynchronous sends? You've got to think, you're saying to MPI, please deliver this message. Don't tell me when it gets there. I don't need to know, but I need to be able to reuse that data straight away because I need to reuse that. I can't waste memory. What is the only way you could implement asynchronous send to get the right answer? Or maybe overcomplicating the question. But the hint is in the name of the send routine. What does MPI have to do with that message when you give it to it? It has, yes, it has to store the message somewhere temporary. Exactly, Joe. It has to buffer it internally. So the reason that MPI calls asynchronous send buffered send is to say, look, what is happening? If you think about it, it's the only way it's possible to implement. MPI has to take a copy of this. So when you call an asynchronous send, a buffered send, MPI says, right, thanks very much. I've taken a copy. You can carry on. Okay, so that's important. A receive completes when a message has arrived. A receive is always in that sense synchronous. You issue a receive and you wait for the message to arrive. The confusing thing about MPI, and I've got a whole lecture on it later on today, is that standard send, which is the send which you would think you would normally use because it's the standard send, can either be synchronous or buffered, and you don't know which. This causes enormous confusion. It's the most misunderstood thing in MPI, but for the moment, so the reason is in this. So here are the calls. Standard send is MPI send. So does this mean that synchronous send does not store the data in extra buffer? Probably. It could, but it is possible. It doesn't have to. So you cannot assume that it does. Put it that way. It's possible that it might, but I mean, as a pure, if you're taking a pure view and not worry about horrible implementation details, as a pure implementation, no, synchronous send does not store the data in an extra buffer, okay? Because you're not allowed to assume that. Of course, it can do whatever it likes under the hood, but your model should be that synchronous send, exactly as you said, synchronous send does not store the data in a buffer. That should be your model, okay? And that becomes very important when we talk about non-blocking communications. We'll come back to it. So your model should be that it does not make a copy of the data. It's operating on the data which you've given it, okay? So standard send is MPI send, synchronous send is MPI S send, buffered send is MPI B send, and receive is MPI receive. Now, unless I say otherwise, you should always program with MPI S send, okay? Because we know what it does. It's synchronous, okay? You issue a synchronous send, it will not return control to you until a receive has been posted and the message has been delivered, okay? MPI B send is hard to use. MPI send is ambiguous. So when you're learning MPI, program with MPI S send and MPI receive. So in any of the exercises, unless I say otherwise, when I say send, I mean S send because we know what it does. Trust me on that. I'll come back later today to explain the intricacies behind why MPI send seems to. Why does MPI send exist? I have a whole lecture on that at the end of the day. Okay. So it's a very good question, and I try and explain. Yes and no. SN doesn't act like a barrier because a barrier is across a whole communicator. A barrier would synchronize all the processes in the communicator, which could be a million processes. SN is like a barrier between a pair of processes where when the send and receive match, it's like a barrier. Does that make sense? So yes, there is synchronization, but a barrier is a more global thing. Okay, fine. So how do we send them? I've finally got some syntax. Okay, so MPI S send. I can't get my little highlight. We specify a buffer, which is the send buffer. We specify count, and we specify a data type. So that might be, here's an array, and it's got 53 integers, okay? We specify destination, which is where we want it to go. We specify a tag, I'll come back to a tag, and we give a communicator, which is the communicator in which this communication takes place. For us, that will currently be MPI com world. Fortran is just the same, except in Fortran, we have buff, count, data type, dest, tag, com. We have an extra IR variable. All of these parameters are integers, okay? They're not parameterized, at least in the Fortran 90 interface, like they are in the C. And this type buff star is a pseudo syntax to say, this is an array of any type. Now, this is where it gets a bit hairy. In Fortran, it is illegal to pass a variable of undefined type. Okay, it is not. However, MPI decided they'd have a single send routine for all types. So, but this does cause some confusion. In C, you just say void, which it's a complete cheat. It says, oh, I don't care what it is. Could be anything. Don't bother. Fortran doesn't have a void. Fortran's a very purist language, very pedantic, and it has its plus sizes. But here, it just means it's some data. Okay, this means that MPI Send is an illegal Fortran routine. Okay, but we'll just hoodwink the compiler. Okay, well, that has some ramifications, but don't worry about it. Unless you're a real Fortran purist, at which point you're probably now having a heart attack. But so it's much more easy to see examples. Okay, I want to send data from rank 1 to rank 3. So first of all, I declare my array, int x 10, so I have an array of 10 integers. Okay, I then do MPI send. I want to send x, which is 10 integers, to rank 3, which is the destination. I specify a tag, and I specify communicator. Okay, now the tag is extra information. It's a bit like, it's some extra, so it's a bit like an envelope color. You know, for example, when you get a message, if you get bills in the post, they're red. So a tag is an extra piece of metadata you can attach to a message. You may or may not use it. We'll come back to its uses later on. You have to specify it, but if you don't care about tags, just specify tag equals 0. Okay. Okay. Now I want to send data from rank 1 to rank 3. Okay. I may have revealed the answer here, but what does this code do? I want to send data from rank 1 to rank 3. If I run this on 4 processes, is that what happens? If I run this code as written on the screen here on 4 processes, what actually happens? Who calls the send? Yes, every process calls the send. All processes are trying to send to process 3. So this code is guaranteed to deadlock for 2 reasons. First of all, every process is doing an send, so nobody can get to a receive. But in particular, process 3 is doing an send to itself. Okay, process 3 is phoning itself and say, why is it engaged? Phoning yourself, of course it's engaged. So what do we do if we want rank 1 to send to rank 3? What do we have to do? And yes, Chris Bradley, 3 tries to send to 3, but now it is legal to send a message to yourself. If this was an asynchronous send, if this was buffered, it's fine. You can send a message to yourself. But the fact it's synchronous means you're waiting for the receive. So you have to put if rank equals 1. Okay, so that's really important. Okay, in Fortran, for a scalar, okay, because MPI expects an array. For a scalar, you just pass the address and say it's 1 integer. Okay, so if you have a scalar index, you do the address of x. Okay, so is that clear? That's quite. I'll do the Fortran now. Now Fortran, okay, integer dimension 10x. If rank equals 1, old-fashioned syntax, call MPI send x10 MPI integer 3 not MPI combo I error. And in Fortran doesn't differentiate. Well, it sends everything by reference, unless you're a Fortran purist. Scalar is just an array of length 1. So we can, if we want to send a scalar, we just say x1 integer. We don't have to do the funny dereferencing. No, you know what I mean, pointer stuff. So is that clear? Okay. So the fact we say MPI integer here, sorry, is because we've declared it as an integer. It's up to us to tell MPI this is an array of integers, okay? Because otherwise, well, what would go wrong if I didn't tell it was integers? If I said this was an array of doubles, call MPI send x10 MPI double precision, but it was declared as integers, what do you think might happen? Why does MPI need to know what the data is? Exactly, the size of the array will be wrong. Absolutely. So MPI has to know they're integers, because to send 3, if they're integers, it knows that they're 4 bytes. So it knows the first 4 bytes. So if you said send 3 integers, it sends 12 bytes. If you told it to send 3 double precisions, it would send 24 bytes, and that would read off the end of your array. So it's up to you to make sure that the definition, and this is where you lose out. If MPI were a compiler, you wouldn't have to do this. If MPI were a compiler, it isn't a compiler, it's just a bunch of library routines which somebody wrote last year and compiled on your system. Okay. If MPI were a compiler, you wouldn't need to do this because the compiler would say, oh, X is integers, okay? But this is the price you pay for having. Now, overall, having it as a library is a good thing, okay? But so multi-dimensional arrays, I'll come back to that. So are you Fortran or C, Luke? So Fortran is easy. If that was integer dimension, I should have that as an example here. If this was integer dimension 10, 10x, you just do x. You would just say it's 100 integers because it's 10 by 10. So in Fortran, multi-dimensional arrays are easy because arrays are a part of the Fortran language. They're guaranteed to be contiguous in memory. You just say how many elements there are. You don't say the MPI type. So the type is the base type. We'll come back. There's more sophisticated. Yeah, right. So Fortran programs are for C programs, anything to do arrays is an absolute nightmare because the way that C does or doesn't do arrays is a complete disaster. Has been since it was written 40 years ago. Fortran has its other issues, but you know, in terms of arrays, there is no comparison. So if you do vector and you need to so MPI assumes it's contiguous data. You need to flatten the arrays. Now, the trick is to make sure that your arrays are already flattened, and I'll cover that. The trick is to use data types, to use structures where if it's a 10 by 10 C array, those 100 elements are stored contiguously, and then you can just send it as a single type. If you try and use what you might call, I think these are ragged arrays, if you try and use other higher, it's pointers to pointers, and it's just a nightmare. So yes. You can either flatten, but the trick is to make sure you have data types which at the start are. It's like NumPy, okay? That, you know, in Python they say, look, if you're actually a scientific and technical programmer, don't want any of these stupid Python lists. You want proper arrays, and we'll define a new type called in NumPy, which allows you to have these things. It's a question of using the right data types. I'm not a C++ programmer, but I'll talk about that in the context of C, which hopefully illustrates it. So the receive, we specify receive buff count data type source tag com status. So the only difference here is that we say I want to receive from the source. I want it to go into this buffer with this count of this data, and I have to specify this status. Okay, the status in C is a structure, and I pass a pointer to it. This is the other place where C and Fortran diverge. In MPI, in Fortran, the status variable, which is the envelope information, is an array. The number one error that Fortran programmers make is they specify status as being a scalar, not an array of size MPI status size. Now, MPI was defined before Fortran had the effective structures, derived types. The modern 2008 interface has an MPI com type object, and I'll cover that tomorrow. But in standard Fortran, the way most people use it, status is an array. If you're a Fortran programmer, you might say, well, hold on a minute. Fortran should catch this because Fortran will say receive is defined with status as a scalar, as an array, and you've passed me a scalar. But because this is the totally illegal Fortran routine in the first place, because buff is of any type, the only way you can get this past the compiler, at least in the Fortran 90 interface, is to turn off all this stuff. So yes, the buffer must be pre-allocated on receive. And now you're going to ask, how do I know if I don't know how big the incoming message is? I'll come back to that. That's a very good question. But that is, I will come back to that. But yes, the buffer must be pre-allocated on receive. So I want to receive data from rank 1 on rank 3. So rank 1 has to be MPI receive. So I have int y. In C, the status object, the metadata is a little structure, MPI status. So I want to receive y, 10 integers from 1, and the tag has to match. So you're saying, I want to receive a message from rank 1, and it must have tag 0, okay? Put the data here, and putting the metadata here, okay? And of course, we have to protect this with rank equals 3 because I only want rank 3 too. And with the scalar, it's exactly the same, okay? That's right, it's the same trick. We pass the address. I'll do the Fortran one now. In Fortran, you to interdimensional status size status, you have to specify the status here as a little array. In C, it's a structure with lots of elements. In Fortran, it's an array with lots of entries. It's just a choice. So that's pretty clear. Okay. Does anyone have any questions about that before I ask? I'm going to ask another question, but if anyone has any questions about that, please ask. Okay. What do you think this 10 means? Interdimension 10y, MPI received y 10 integer, and remember the send was sending 10 integers. Where was the send? There we go. We sent it. What does that 10 mean? Sorry. So no, remember, you remember MPI init is just a function call, so it has no, status is a Fortran variable, so you can declare it anywhere. That you can't alter whether or not you can declare a variable in C or Fortran, whether you. So it's just, you just declare it wherever you want, but it can be before or after MPI init. MPI init is just a function call, so status is defined in the header file. Does that make sense? So in Fortran, this variable, where's the Fortran one? This variable MPI status is just a constant. It's just a constant in the header file, and in C, this MPI status is just an alias for a structure which is defined in the header file. Does that make sense? You can declare it after MPI init, but it's just a variable. Okay, fine. So what do people think the 10 is? What does this 10 mean? It's not obvious. Process 1 send 4 into 3, can 3 take only? So I'm going to cover that. Okay, fine. So Laura, I'm going to answer that question. So 10 is the size of the incoming data in integers. So that's what any normal person would think. It's not. What you're technically saying, so that's what most people think, but what you're saying is, I want to receive some data from rank 1, and I have reserved enough space for 10 integers. Okay, that is what you're actually saying. Now, in many programs, the incoming message is size 10. Okay, but technically what you're saying is here, I'm going to receive a message from rank 1 with tag 0, and I have enough space to store a message of size 10. Okay. Now, if the incoming message is larger than 10, you get an error. It is illegal, and your program will burn. Okay. So if the incoming message is too large, you will get an error, and your program will stop with an error. MPI is very bad at reporting errors, but this is one of the few cases you get. It will say incoming message truncated bomb or message too large. If the incoming message is smaller than 10, that's perfectly legitimate. Okay. So Laura said if process 1 send 4 into 3, can 3 take only 2? No, it can't. You can't, you have, so in MPI, this is another point, MPI isn't a pipe model where you have a pipe between two processes and data. MPI is based on, you send a message and it has to be received or not received in its entirety. So the minimum unit is a message and all its data. You can't pick and choose, okay? So you might now say, well, okay, so I issue that receive, okay? It returns, which means that the rank 1 sent me a message which was of size 10 integers or less or fewer. How do I know how long? So how do I know how long? So all I know is I've received a message which was 10 integers or fewer integers. How do I know how many integers actually came in? Where do you think that message is stored? In the state. Now, many programs, in many programs never look at the status because your messages are always of size 10 or size 1. Often you have fixed sizes, but in general, I'll come back to that. The process is synchronized. So as someone mentioned before, it's like a mini barrier. The sender process specifies the synchronous mode. It's blocking both processes, waiting until the transaction is completed. The sender must specify a valid destination rank. The receiver must specify a valid source rank. The communicator must be the same. The tags must match. The message types must match, and the receiver's buffer must be large enough. So asking for a particular tag is a requirement. So if in this case rank 3 sent an integer message of if rank 1 sent a message with tag 5, this would ignore it. It'd say no, I'm not waiting for a message from tag 5. I'm waiting for a message of tag 0. So the source and the tag are requirements, and they must match for it to complete. So you might say this looks like overkill. It's like a port. Well, it's not really. I mean, a port is sort of an always open thing. It's basically, when I write a letter, I write a header. I say from this to so and so. Yeah, it's that little. It's like it is just the header information on a letter. Who sent it? The date stamp, maybe. I mean, that's that kind of thing. Yeah, for the attention of. It's really just that envelope information. It's a header, effectively. It's the header. It's like a packet header. I'm not a networking person, but you might say this is overkill because I have to match on communicator and match on tag. But the important point is you can wildcard. So you can wildcard on MPI. You can say, I want to receive message from anybody. So instead of specifying a source, you say MPI any source. You can receive from any tag. You say MPI any tag. But you cannot wildcard on the communicator. So communicators are absolute guarantees of message isolation. Okay. So we'll come back to that. But you can wildcard on tag and source. And if you do wildcard on tag and source, the actual source and tag for all, what do you mean by all? I didn't quite understand the. Well, MPI any source means all sources. It will accept. So this still only matches one send. Okay, so it's not all. It is any. There is one receive matches one send. If you want to receive lots from everybody, you have to issue lots of receives. Does that make sense? So any one send only matches one receive. So MPI all source would actually be maybe it's like star, but it matches a single one. It doesn't care who it is. The actual source and tag are returning the receiver's status parameter. Okay. So as I said, the communication envelope, the metadata, which is like this stuff here, goes into the status, and the actual data goes into the receive buffer. So the envelope information is returned from MPI receivers. Many programs never look at the status because you've matched your sends and receives are of constant size, but you need to know that it's there. So if you did a wildcard on MPI any source, you need to know who sent it, because if I'm doing this controller worker thing, I would say, look, I've just sent out lots of work. I don't know who's going to finish first, so I'll issue a receive from MPI any source. A message comes in, I say, thank you very much, but I need to give that person more work. I need to know who it was that sent me that. So that is stored in status.mpi source in C, or status, or the MPI source element of the status array. So the status array might be of length 6, and the MPI source is stored in the 3rd entry. I don't know. All these numbers vary implementation by implementation, but that's what you should think of. The tag is the same. It's directly accessible in the structure of the status in C, or it's this particular element of the status array in Fortran. For technical reasons, which I can come back to if you want, the count, which is the size of the incoming message, is not available directly. You have to call a helper routine. You have to call a routine called MPI get count. You have to say, here's the status, okay? How many integers were in that message, or how many doubles? you can think about it as saying it's not quite true, but it's almost true. You can think about it as saying MPI only knows that it got 12 bytes, okay? Sorry, 16 bytes. If you say how many integers, well, it say that was 4 integers. If you say how many doubles, it will say it was 2 doubles. It's not quite that simple, but it's similar to that, okay? So it's annoying, but the count, which is actually the thing you often want to know, is not available directly in the status. You have to call a helper function. So the int in the procedures return is an error code. But in practice, the default behavior for MPI on error is to crash, so it never returns it. Now, I should actually, this should be here. So so if you are, sorry, this is, so I should have had this in the slide, I don't, but there are lots of return codes, I don't even know what they are, but successful is MPI success. So all you need to check is if error is not equal to MPI success, then crash, then die. However, in reality, MPI will already have died. You can override that behavior. You can tell MPI to return on errors and not die. But on any error, the status of MPI is undefined. So if there's any error in MPI, it's unsafe to continue anyway. So you just have to quit. But if you're careful, you will check whether error. I should really have this on the slide. That's an omission. Apologies. A successful call to MPI returns MPI success. An unsuccessful call will either crash or return an error which is not. I don't even know what they are because in practice, it's not useful. MPI is not very good at giving you information on errors, other than that they happen. It's very good at detecting there are errors and very good at bombing out and saying there was a problem, but giving you more information is bad. So that's an omission in the slides. Apologies, I should have that in the slides. So I have some slides here on message order preservation. I'm not going to cover this, but because it takes a bit too long in this. But messages don't overtake each other. Now that is a meaningless statement between pairs of processes. Messages don't. That's a meaningless statement for synchronous send, because with synchronous send, it's like saying do 2 phone calls overtake each other. I can only make 1 phone call. I phone somebody, I speak to them, I put it down. Okay, but if you say, well, I'm sending emails or letters, okay. Do they overtake? So in everyday parlance, in everyday experience, if you send 2 letters, send 2 emails or post 2 letters, order preserved. Yeah. If I'm on holiday and I send my mum 2 postcards, does she get them in the order I sent them? If I send you 2 emails, do you get them in the order I sent? It's not. Oh, let's stick with letters. If I'm on holiday, I send my mum 2 postcards, does she get them in the order I sent them? Yes or no? Does the Postal Service guarantee message order preservation? Maybe. In other words, no, it's not guaranteed. It's not guaranteed. MPI does guarantee message order preservation. MPI guarantees if you send 2 messages in a particular order, they will be received in that order. Okay? Message order preservation is guaranteed in MPI, even for asynchronous sends. The reason this is important is the network is probably a packet network, and in the hardware, the messages may overtake each other. Okay? But MPI guarantees a higher level. If you issue 2 sends and you issue 2 receives, they're matched in the right order. It's quite a subtle point, but if that were not true, it would be very hard to write correct programs. The fact that MPI preserves message order is actually quite a strong, that means that writing programs is easy. If it weren't true, it would actually be very hard. You'd have to tag all your messages to check there. So it's actually, it sounds like a throwaway statement. There are subtleties to that which I'm not going to cover, okay? Because it's too much for the moment. I may come back to it if I have time later on. So the exercise is the calculation of pi. It illustrates 2 things. It illustrates how to divide up work based on rank and size, and it also illustrates point-to-point send and receive. It's quite a simple exercise, but it illustrates a surprising amount of issues in MPI. So I will spend at least maybe 2 minutes going through the sheet, and then we have at least half an hour for the practical. So I will, unless there are any questions on that lecture. So I was, this is what I talk about. No. So if two messages are sent from different sources to a destination with a wildcard, are they guaranteed to be in order to send? No. MPI has no concept of global time. And in fact, if you wanted to do that, it would be impossible, because MPI would receive a message from rank 3. Okay. Imagine it has to receive them. Say, well, actually, maybe rank 2 sent a message earlier than this. Okay, which has got delayed in the network. It would have to wait an infinite time to guarantee. So actually, it is not possible, in other than having some central point of control, which you can't have in MPI, in a message passing system. It's not sensible, practically possible to guarantee message order preservation from different sources. This is a statement about a point-to-point pair of senders and receivers. So if you wanted that, you would pay an enormous price in performance, because every message would have to be logged in a central database. And it would make your performance be 1,000 times, 1,000,000 times slower. It wouldn't work. It's a very good question. It's a bit of a subtle point, but no, it is not guaranteed. But very, very, very few MPI programs. So things about performance, yes, we'll talk about this later on. Actually, not wildcarding. To be honest, wildcarding is a bit of an issue. We would actually use something called non-blocking communications, which I'm going to talk about tomorrow. So yes, if you're receiving a lot of ranks, it is not a good idea to mandate the order. But actually, the best way to do it is through something called non-blocking communications, not wildcarding. But you're right. You've got the essence that mandating the order, saying I'm going to receive a message from process 1, then process 2, is a dumb idea, because maybe process 93 is already finished. But actually, the right way to do that is to do it with well, you can do it with MPI any source. We can talk about it once I've talked about non-blocking communications. You will see the two options that you have, and we can discuss that. It's a very good question. Okay, fine. So if I now go through the sheet, let us so what I really should do, I need multiple browsers. I need a browser which is dedicated to sharing content, so you don't accidentally see my emails and that. So let me a second. Share content. There it is. So that's a bit. Can we zoom in maybe? The font rendering in GitHub is pretty poor. But anyway, so this is a parallel. You can expand pi by 4. This is one of these. This is an integral, and this is a very dumb expansion of just dividing the it's not even Simpson's rule. It's just dividing up into pi, just errand. It doesn't matter where it comes from. That pi by 4 is equal to 1 upon n, sum I equals 1 to n, 1 over 1 plus I minus half over n squared. Okay, so I want you to use this where n is a large number, like 840, and you run on. So n is not the number of processes. N is a big number, 840, say, and you're running this calculation in parallel on, say, 2, 3, 4, 5, 6, 7, 8 processes. I've picked 840 because it divides by a lot of factors. Don't bother about the case where it doesn't divide exactly. That's just a complication. So I want you to modify your Hello World program, which already computes the rank and the size, so that each process independently computes the value of pi and prints it to the screen. Okay, so please write this program first so that you get the right value of pi when it's not parallelized, because this is not trivial. C programs will get this wrong. This I is not 0 to n minus 1. This is 1 to n. Okay, when it says sum 1 to n, this is not just a counting loop. Sorry, you can't see my cursor. That's unfortunate. And maybe I have to change that so you can see my cursor. This is not a counting loop. This I value enters into the calculation. We parallelize this because this is summation. So for example, we could say On two processes, rank 0 would do I equals 1 to n upon 2, and rank 1 would do n upon 2 plus 1 to n. Now, of course, your program should work for any number of ranks, not just 2, but that's an example. So you should then write that, so you have each process computing a separate portion of the sum. So you've checked that if you run it serially from 1 to n, you get the right answer. The second one is you've checked you split up the loop limits correctly, and then add them up by hand with a calculator to check you get the right answer. Now, now we want to accumulate these partial sums by sending them to a master. Now, in a real program, you would do this using a reduction operation, a collective, okay? So I did arm and ah about having this exercise, but it's a very, very useful learning exercise. So all processes except the master, which we'll say is rank 0, send their partial sum to the master. The master receives the values from all the other processes, adding them to its own partial sum. You should use MPI send and MPI receive, okay? So, and then you should be able to compute pi in parallel on multiple processes. Each process computes a partial piece of the summation, and then you bring the values together and add them all together, okay? Is that clear? Now, I've talked about timing. I'll come back to that because that's a bit much for the moment. Timing parallel programs is a bit of an art. You can read that if you want. MPI time is a function which records the time. It gives you a clock, not a global clock, but a clock on each process, which gives you a wall clock time, and you can subtract it. So I've talked about how to work it there, but I would ignore that for the moment. The really thing is to start doing this pi example. So does anyone have any questions over this? It's not as it's you may find it straightforward, you may not. It is deceptively hard. Can be deceptively hard. So are there any questions about the pi example? So we'll do the pi example now till 3:30, till 3, apologies. No, 3:30. From 4 till 4:30, or 4:45-ish, I will give a lecture called Communicators, Tags and Modes, which goes into some detail about what the heck is MPI send for. If you don't know if it's synchronous or asynchronous, why is it there? Why all this confusion? Well, I try and explain the logic behind it. Hopefully it makes some sense. But we'll come back to the pi example. So don't worry if you don't get the pi example finished in the next half hour. I don't expect you to be able to do that. We'll come back to it after the Communicators, Tags and Modes lecture, which is from 4 till just about 4:30, 4:45. But the first thing I'll do tomorrow morning, if you look at the timetable, is I will go through in gory detail, fairly verbose and complete solutions to the pi example, because although it's very simple, it illustrates a certain number of interesting or key features about MPI. Okay. You also know enough to do, if you can do send and receive, you can do this broadcast and scatter exercise. You can also do this ping pong exercise. It's up to you. I put these in, this one is new, I put this in recently, ping pong, but I really, there's a lot there, but the pi example is really the key example. If you can do the pi example, the only bad thing about the pi example is it doesn't illustrate sending messages of more than one element. That's why I put in these other ones. You're always sending and receiving messages of one double precision. So that can be a bit of an issue in terms of generality, but it is a very useful program to write, and that's why I have these other exercises, which as I said, involve bigger messages. Okay. So if there are no questions about the pi example, then please get going or do what you want. Me and I think it's Julian, I think, is around this afternoon. I can't. Yeah, Julian number 3 is around. I don't know if that's different from Julian number 1, but so Julian is around to answer your question. I'll try and stay around. I may have to take a quick break for a glass of water, but the main thing is we will definitely be around till 3:30. From 3:30 till 4 we may be away, but I will start lecturing again at 4. So we will be around until 3:30, guaranteed, me or Julian, to answer your questions. And then from 4, I'll put a slide up about it. I will start lecturing again if that's okay with everyone. Oh, you got some failed log. Was that a bandwidth issue, Julian, or was it just a flaky collaborate? It did seem to be having a few issues with some people this morning, although it's generally quite good. Okay, so I will now fix up the slide, and so guaranteed I'll be back talking to you again at 4 o'clock. And so there's no point you setting up Slurm on a home laptop because it won't give you any. It's much easier just to do MPI run. You only have one node on your laptop. So why did you want to do that? I mean, I think Slurm free. I don't. But Slurm is only used when you want to run a program. Okay, it's free, is it? Okay, I would. Well, hopefully next week we'll be back on Cirrus, which has PBS. What I'm going to do is hopefully in the next hour I will put up instructions on the crib sheet for how to run parallel jobs on multiple nodes using Slurm. My colleague Adrian, as you saw, I was able to do it myself. You should be able to do that as well. I'll just put that stuff up there, so you'll be able to use Slurm on NextGen IO. I don't know if you're using NextGen IO, Dale, but that is what I will. I've assigned you an account, so you should be able to get. I'll put instructions on the web, hopefully before 4, if I get time, on how to use Slurm, if that's okay. Okay. But as I said, this was all done at a great rush. So normally, if we were running a course, we would have a dedicated queue, because the problem is if you submit to the queue, your job is in the mix with all the other users. And if the system is busy, the batch system may not run it till tomorrow. So for a normal course, we would have a dedicated course queue. However, this NextGen IO system is actually a kind of research machine, and it's not heavily used. I mean, it's very important. But it's not a production machine. So it's not used for big production runs. And yes, that's exactly why I hesitated when I talked about Cirrus, because as Julian says, Archer 2 will use Slurm. So actually, yeah, that's a reason for learning Slurm. Although when I say learn Slurm, I mean batch systems are, you copy somebody's script and you change a few parameters till it works. I mean, I know I would never, ever, ever recommend someone wrote a computer program in that way. I don't believe. But batch systems, you don't read the manual, you get one that works and you edit it, because there's always some random magic statement which makes no sense. Here you have to say export QZ53 equals 95. Okay. So yes. So I don't know if that was you or Andy, but a few EPC people have put up some pretty good. The good thing I think about Slurm is that it tends to be fairly universal. PBS, different systems look very, very different. Whereas Slurm, there will always be a few tweaks locally, but to a large extent, Slurm apparently looks the same on most systems, whereas PBS could look very, very different. It's a long story as to why that was the case on Archer, but they've gone to Slurm, which I think is a good thing. Okay, so I'll shut up now and let you get on with the exercise, and I will put up a back with you soon.